We will now be seeing the solution for the modeling of a vibrating elastic string using the separating variables method. So the model of a vibrating elastic string has already been shown to be it consists of a PDE that is something similar to this. T squared equals c squared times du dx squared, where c squared is equal to t over rho. And since the string is fastened at the ends x equals 0 and x equals L, we have some boundaries conditions where the fluctuation function of the string at x equals 0 is equal to 0, and at x equals L is equal to 0 for all t's major or equal to 0. That means that the string will not fluctuate at the limit of the string. That means where x is equal to 0 and where x is equal to L. And because the motion of the string depends on the initial fluctuation, that is the force that started the vibration of the string fluctuation. T equals 0, we call it f of x, and it depends also on its initial velocity, that is at t equals 0, and we will call it g of x. So that means that the fluctuation function at any point x when time is equal to 0 is equal to a fluctuation method f of x, and that the velocity of the fluctuation at any point x at the time equals 0 is equal to a velocity function called g of x, where x goes from 0 to L. That are the boundaries of the motion of the string. So we can then define some steps in order to establish the modeling of the vibrating string, where we have the step 1. It's called the method of separating variables. By setting u depending on x and t equal to the product of two different functions, one f of x and g of t, one depending on x and one depending on t. So with this we obtain two ordinary differential equations from the originally partial derivative equation, one evidentially for f of x and the other for g of t. That's step 1. Step 2, we determine the solution of the obtained ordinary differential equations that can satisfy the boundary conditions. That we have already established. And as a step 3, using Fourier series, we compose the solutions found in step 2 to obtain a solution of the original partial derivative equation satisfying both the boundary condition but also the initial condition. So let's start analyzing the first step. So step 1 is setting two ordinary differential equations from the wave equation. So we have to determine solutions of d squared u dt squared equal to c squared d squared u dx squared, where c squared is equal to t over rho, from a fluctuation method u x comma t equal to f of x multiplied by g of t. So we can differentiate and we can obtain that d squared u with respect of t squared is equal to f g double dot, and that g squared u depending on x squared is equal to f by prime g. This is just a notation to understand that we are deriving 2 times with respect of time and 2 times with respect of x. Then we know from the original partial derivative equation that f times g double dot is equal to c squared times f by prime times g. So we can divide by c squared f g, which gives us g by prime over c squared g is equal to f by prime over f, and this is equal to a given constant. And therefore, f by prime minus kf is equal to 0, and g double dot minus c squared kg is equal to 0. So we can now solve for using k equals minus p squared, where p is actually a given period of the oscillation, n of times pi over L squared, this is minus. So we obtain something like this, g by prime plus lambda n g squared is equal to 0, where lambda n is actually equal to c times p, where This can also be represented by C times n pi over L. That is just the period. So with all these, we can obtain a general solution. It's given by n of t is equal to Bn cosine of lambda n t plus Bn star times sine of lambda n t. That is just a representation of the oscillation with respect of time. Hence, solutions of the PDE satisfying the boundary conditions must be of the way u n x t is equal to fn x times gm t equal to gm t times fn x, or right, developed in another way, un x t is equal to vn cosine of lambda n t plus bn star sine of lambda n t times sine of m pi over L times x, where n goes from 1 to 2 so on. So this can be a specific way of defining the solutions of the partial derivative equation that satisfy the boundary conditions.